so loudly. Okay, so now we will switch gears from multi-messenger astrophysics to dark matter searches with astrophysical data. Okay, so I'll have just a short introduction, but very brief, just to say that as far as dark matter is concerned, we are quite convinced. I mean, we are convinced that it does exist. It's out there. It's essential building block of standard model of cosmology, everything that we know in cosmology, and we know that on very different scales, like starting from hundreds of megaparsecs, where here each dot is a galaxy, to small dwarf galaxies. We have evidence the dark matter, meaning some fluid that does not shine, does not interact with photons, is present. But all evidence we have so far is gravitational, meaning it comes from the way such fluid interacts with normal matter gravitationally. So we do not have evidence for any other kind of interaction. And of course, all evidence is astrophysical. I mean, covers, say, hundreds of megaparsecs to kiloparsec scales. So this is where we have enough data on motion of normal matter, and to the way how normal matter moves or clusters, we can deduce that there is some gravitational pull that it feels from this dark matter fluid. Okay, but then what it can be? So that's the big question, and we have, little knowledge, given that we only have gravitational interaction so far. So if one thinks on what it could be, given what we know about normal matter, then one gets, a very wide range of opportunities. So for example, it could be a particle. Our world is made of particles, so it could be a new particle that sort of completes the standard model, and then there we could go from sort of micro electron volts to hundreds of TeVs or PeVs particles. If you go to lower masses still that are not excluded, that could be a new particle, but its wave nature should become important here. So this is not excluded. This could also be, but that has consequences on what other properties besides gravitational we expect from such dark matter. Also, it could be just macro objects. It is not necessary that it is a new particle. It could be so-called primordial black holes or various types of compact objects that somehow do not shine but are present in the universe and are responsible for this gravitational pull. So just few pros and cons in looking for dark matter through astrophysical probes. So if you look in astrophysics to find dark matter, okay, you have pros because you're looking in faraway objects in places where we have evidence for dark matter. So dark matter is there, you just try to find it differently than it has been already measured. And we now, of course, have plenty of astro data, as seen also in the previous talk. So this is sort of a right time to look for it. Cons are, of course, that we are learning backgrounds, meaning all astrophysics, as we are searching for dark matter. And so this is very hard, but it's also interesting for us dark matter people, because we have to know all this astrophysics, model it properly, and then maybe look for some accesses over those backgrounds. Of course, everything is model dependent, as in astrophysical modeling. So a word of caution, of course, as I was saying, as we are looking for as we are trying to figure out astrophysics, as we look for accesses that could come from these new particles or new objects, dark matter, we are bound to have some discoveries as well, like some accesses that we do not know what they are, could be dark matter, but could also be just astrophysics that we do not know. And so, as you're all probably very well aware, so this is very old plot, but sort of summarizes all the sort of dark matter discoveries, not very robust, but hints of dark matter discoveries that happen, in this period in 2010 to 2015, say. So these things do happen. Sometimes we can resolve them. We can say this is astrophysics actually, but sometimes they just remain open because we could not be sure, as you will see in the example here. Okay, so how do we look? So of course, because we have all these, because we have all these opportunities, we have to look in many, many ways. It's unfortunately not just one search fits all. And so we could divide the searches in several sort of approaches. One is that we could look for signatures in which dark matter injects cosmic rays. Okay, so then you look in cosmic ray data, broadly speaking, and try to find for some emission that cannot be explained with astrophysical sources, which is of course not trivial. So that could be, for example, the dark matter particles interact with each other, okay, and produce these cosmic rays, meaning stable particles, neutrinos, gammas, charged cosmic rays. So this is particular class of models called the thermal dark matter that I will tell you more about. Then dark matter itself as a single particle could convert to cosmic rays. It could be sort of decays of dark matter particles to lighter particles, or conversions. So these are, for example, so-called axion-like dark matter that in the presence of magnetic fields converts to photons, for example. So this would lead to a different kind of search. Or, for example, if dark matter is macro objects, primordial black holes, those would evaporate and produce standard model particles, again, that one could look in cosmic rays. Different way to look is the dark matter on its own could alter behavior of astrophysical systems. For example, it could be captured by stars, altering stellar evolution, for example, causing stars to collapse sooner than they would otherwise. It could be captured in planets, where it could annihilate and alter internal heat production of planets, for example. It could alter cooling of stars via dark matter channel. For example, supernova collapses, it could produce axion-like particles that would escape and bring energy out of the star. Or it could affect gravitational wave emission. For example, if you have so-called dark matter dresses around black holes, that would affect production of gravitational wave signals. Or if you have so-called ultralight boson superradiance regions around black holes, that could also affect gravitational waves, that we measure. And we could look in those channels also for signatures of new physics. And then lastly, we could continue looking in these purely gravitational signals that we looked so far. So before I told you we have gravitational evidence that dark matter exists from hundreds of megaparsecs to kiloparsecs, now we could try to push it down. We could try to look on smaller and smaller scales and see if suddenly dark matter disappears, then that scale would tell us something about dark matter properties. So here one can look at gravitational lensing, or for example, this is also interesting search that was sort of made possible by Gaia, but will be in the future even more interesting with Vera Rubin, is that if one looks at stellar streams in our galaxy, passage of a dark matter clump in our galaxy would disrupt stellar streams, and one could look for then small clumps of dark matter in our galaxy that way. Okay, so this last kind of search borders with cosmology, because there you have probes at different redshifts that then constrain dark matter different scales. So scale and dark matter mass, halo of dark matter from the dark matter are related. So here you constrain smaller and smaller dark matter clumps as a function of redshift with different probes. Okay, so this was all very general, and it's also summarized in this plot from UCAP white paper, where you have all these models and different probes, that I was mentioning that could constrain it. Being this a cosmic ray conference, and from my personal bias, I will focus on these probes that can look for dark matter via direct cosmic messengers, and in particular, I would focus on those that are gamma rays and cosmic rays and neutrinos. And those, as you see, could probe in particular this TV, sort of GV to TV range, then mass of dark matter that would be in micro electron volts that are so-called ALPS, axion-like particles. It also probes primordial black holes, but I will not talk about that today. So of course, how to look? We have all these gamma rays, neutrino, charged cosmic ray probes that you heard a lot during this talk. As I was saying, I will focus on gamma rays, but also radio, X-rays, and so on are very relevant in these searches. So what is expected dark matter signal? Just before we enter into this, is of course that if you look in flux of cosmic rays coming from dark matter, it's obvious it will depend on particle physics and on how dark matter is distributed, of course. So in particle physics, meaning dark matter mass or cross-section or annihilation channel will affect what spectra you expect and what overall luminosity you expect. While cosmology, meaning how dark matter is distributed, will also impact the shape of your signal and also its overall normalization, okay? And so you have to take both things into account when thinking about these things. So this is in particular, I wanted to stress here, is that if you look in photons and neutrinos, because they travel in straight lines, then you really do depend on this factor, how dark matter is distributed. That gives you additional leverage, helps you look for distinguish dark matter signals from astrophysics, and you just have more information. If you look in charged cosmic rays, then typically, at least at galactic scales, cosmic rays lose directionality. And so basically what you measure is only spectral flux of charged cosmic rays that sort of mixes up the particle physics and cosmology properties of dark matter with properties of the galactic medium or intergalactic medium. So in this case, if you look in charged cosmic rays, you lose sort of directionality, at least in these TV to PV scales, but still, these are very powerful searches that I will show you later. So what I will be talking, I will focus mostly on gamma rays, because again, they travel in straight lines and have high statistics than neutrinos, so somehow are the most promising among these messengers. But then I will also say about dark matter search with cosmic rays, specifically antiprotons and neutrinos. Okay, so now gamma rays, and in general, so where would we look for dark matter? Again, from gravitational probes, and because baryons follow dark matter's gravitational pull, we more or less know how dark matter is distributed, but then we also need n-body simulation, to see this in more detail. And we know that in our vicinity, the brightest dark matter spot should be galactic center, and then dark matter should have so this is dark matter map, like overlaid with spiral arms of the galaxy. These are not, of course, dark matter structures. Dark matter does not produce such things because it doesn't dissipate, but you have the main halo of the galaxy and then lots of subhalos on galactic scale, and then of course you have this cosmic web, and you can look in all these places where you have lots of dark matter. In particular, as I said, galactic center, and in our galaxy, dwarf spheroidal galaxies, which are sort of baryonic counterparts of the largest of these dark matter subhalos in our galaxy. What tools for gamma rays to use? We heard a lot of nice talks in this conference, from the smallest energies of, GeV, sub-GeV to hundreds of GeV by Fermi, Cherenkov telescopes, HAWK, and then Tibet array and LASSO entering the PV range. Of course, this is how the sky looks in GeV versus TV. So this is all the beautiful astrophysics we discovered with these instruments that, at the same time represents a background for dark matter searches. So it's very different as you move higher in energy, but still there is very nice interplay between lowest and highest energies. Now we have this data that we can extrapolate from smaller energies to higher and sort of predict what our backgrounds are in each of these energy ranges. Of course, the PV era is also there and also could be used for dark matter searches. So for this, so what strategies I was saying, and I was saying I will focus on WIMPs and axion-like particles. So this thermal dark matter that WIMPs are prime example is just saying that dark matter was in thermal equilibrium with the rest of particles in the early universe. So this is a very nice and natural assumption that leads you basically to predict to predict the dark matter, what dark matter cross-section should be, annihilation cross-sections should be, if this thermal assumption is to hold. And so basically for these models that were the most popular for a very long time, they have this very nice handle that are natural and then predictive. And so we know where to look, at which energy and which cross-section scale. The strategies are, as I was saying before, you can either look, for example, in galactic center that has the highest signal strength, but in terms of robustness or how complicated are the background is the lowest. And then other targets, are a little bit fainter, maybe more robust. And on the other hand, edge of things, you have so-called smoking gun signatures, where, for example, dwarf spheroidal galaxies lie, where you have no backgrounds, no gamma ray backgrounds from this object. There is no gamma ray emission measured from dwarf spheroidal galaxies because they're cold and old systems, but they have still a lot of dark matter. So if you see a signal, it would be considered smoking gun detection. So what is the state of art in this world, for these models, is that basically, Fermi-Lat observation of dwarfs excluded. So this is the predicted cross-section, and so it's excluded to the left by Fermi-Lat observation of dwarfs and other targets, and is severely challenged by Hess observations of galactic center. So this is a bit oldish plot. We've seen in Javier's talk yesterday very nice common work between various collaborations where they combine likelihoods to produce a single limit on WIMP models that include dwarfs of Fermi and then dwarfs by Hess, Veritas, Magic, and Hawke. And so this is a new plot. A paper is to be published soon. So in terms of state of the art, there is also, in this other plot, this galactic center excess, these regions that could still be due to dark matter, because in the center of our galaxy, we do have some excess that we yet are not sure or cannot be sure what it is due to. Interestingly, it has properties of dark matter. It has the spectra you expect from dark matter particles. It's very extended, but still cuspy, as you would expect from dark matter particles as well. Very extended, meaning it can be measured up to 10, 15 degrees away from the center. So this is quite tantalizing. Of course, so this would be exactly how we would expect to discover dark matter, with all these properties in the galactic center, has the right cross-section, right mass. However, pulsars are spectral twins of these dark matter models. So 30 GeV BB channel dark matter and pulsar emission is quite similar. So that, and this is exactly the spectrum, more or less, actually, of galactic center excess. And we know now that 300 pulsars, almost 300 pulsars, are discovered by Fermi, though none in the galactic center because it's too far, but still it's very reasonable to assume they are behind this excess. Mattia Di Mauro gave a nice talk on this previously. So on this question, there is still fierce debate ongoing. Is it dark matter? Is it pulsars? What it is? We just do not know at the moment. Definitely, galactic center is fascinating region and lots to be discovered there. So then state of the art is basically, if you don't take into account this galactic center excess, most of this parameter range is probably seems to be excluded or challenged, but TeV window still remains to be explored. So here we still do not have limits that touch expected cross sections. So this is what we would expect for WIMPs, and it's not probed yet. So let me then move to ALPS, axion-like particles. As I was saying, axion-like particles go to gamma rays in the presence of magnetic fields. So here strategies where to look. You want to look in objects with strong magnetic fields that are at large distances that would allow for such conversions. So for example, galaxy clusters are a good target for these guys. And how do you look for or in gamma rays for signatures of axion-like particles. So there are two sort of strong mixing regime between axions and gammas, and outside of that range that could cause two kind of effects. You could have all gammas with probability 1 going to axions converting, and that could affect gamma ray opacity. As you know, if you have a source, extragalactic source, at highest energies, its emission is absorbed by opacity of extragalactic, of low energy photons that interact with high energy gammas. Through electron positron production, pair production. So you expect, so all extragalactic sources have this absorption, but that part could be affected by axions. If gammas would go to axions, they would not be, say, observed. So you would expect, tails or less absorption, for example. This is one way. Other way is that you expect gamma ray irregularities due to this conversion to axions at all energies. And so you would expect that you do not measure perfect power law spectra, but you have irregularities around that. And so this is the search. These are the typical searches that are done. Another strategy is to look for smoking guns, okay? This is something I mentioned. For example, if you would have supernova explosion in our galaxy, you know that gamma rays would arrive after neutrinos because they're trapped in supernova. However, if gamma rays would, if axions would also be produced in the supernova collapse, then those would escape, convert to gamma rays in the galactic magnetic fields, and arrive together with neutrinos. And so if you would observe neutrinos and gamma rays at the same time from supernova, that would be a smoking gun, that there was a channel allowing gamma rays to escape. So this is also a very powerful probe. So for example, now if you look the summary of ALP searches, so this is where ALP dark matter would be, okay? This is the Fermi-Lat search from NGC galaxy to the spectral irregularities, and this is the Hess search. But this green thing is what the sensitivity would be if there would be a supernova while Fermi is in orbit. Okay, so with supernova, this probe would be super powerful, but we need a supernova while we have powerful experiment in the orbit. So this would be very cool, but yeah, so the supernova rate is 1 per 50 years, so we are overdue from 1987, so let's cross fingers that we maybe have such sensitivities soon. Okay, so how about the future? So as I was saying, so these are the Fermi-Lat, these are current Cherenkov telescopes, and then we have the Cherenkov telescope array coming up soon. We have already LASSO building up data for 1 year, as SVGO probably to come up at some point soon. Okay, so what is a CTA? It will have large energy coverage due to 3 kinds of telescopes. It will have also wide energy and almost full sky coverage due to the position in 2 hemispheres, in 2 sites. And it will have more than 60 telescopes, so high sensitivity with respect to current detectors. So status, LST-1 of large telescopes installed in La Palma in 2018. It's still in commissioning phase, ending soon. ERIC is established in 2022, and so construction hopefully should start at a year scale. There was a nice APEC talk covering these points first day. So what is interesting for dark matter searches is that CTA will have dedicated sky surveys of large portions of the sky. It will have extragalactic survey, galactic plane survey, and deep galactic center survey. And so as I was saying, while all of these are very interesting for astrophysics and also for dark matter searches, I will focus on these galactic center surveys. I was saying this is the brightest spot for dark matter. And so the collaboration worked on the paper exploring what would be the sensitivity of CTA to dark matter in the galactic center. And in fact, due to this, taking into account all astrophysical backgrounds, possible systematics, instrumental systematics, and so on. And still, it seems that CTA should be sensitive to to WIMP thermal dark matter in TeV range. So exactly what I was saying before, that there was this window missing, still very motivated window. In fact, we believed, that WIMP should lie here. In fact, CTA will be the one of the experiments one of the rare experiments with the possibility to probe that. In terms of ALPS, if one looks at, again, because CTA will have very good energy resolution, CTA observations, say, of this NGC galaxy in the Perseus cluster would also be quite sensitive and will probe this ALP dark matter region. Okay, good. So summary sort of gamma ray dark matter search is that so that TeV vanilla thermal parameter space is still open, but will be closed by CTA, and that also hopefully LAT and also CTA data are expected to probe the ALP dark matter parameter space. Oh, sorry, this should be cosmic rays. So this is now switching to dark matter search with charged cosmic rays. Here I thought I would be very brief. The point is that, as I was saying before, because we have only spectra to look at, the safest, the back signal to noise is the highest in the anti-particle channel, in antiprotons or positrons. I will just talk about antiprotons because in terms of astrophysics, secondary channel, I mean, particle channels are secondaries. So once when we measure primaries, we should have a good feeling, good model for the secondary production. Of course, modulo many unknowns, but at least it's easier with secondaries. And so then we could look for direct contribution to antiparticles from dark matter in a rather direct way. And so there has been quite a bit of discussion, in fact, looking in the antiproton channel, because as you see, there are some residuals. So if one models the antiproton spectra with a power low, one gets a sort of spectral irregularities or spectral excesses, and in particular, the excess that occupied quite a bit of attention is this one around few GeV in rigidity space. For a few reasons. One, that statistics is quite, I mean, it's not yet, it's not affected by solar modulation much, and statistics is very high in this region. So the excess was quite significant. And if one then plots sort of dark matter limits due to antiprotons, this would be this black line. The limits weaken exactly at this parameter space where galactic center excess dark matter particle could be. So this was also tantalizing a lot, because this is again how we thought we will discover dark matter, first in the galactic center, then in antiprotons and so on. So apparently there is also an excess in antiprotons here. This is a sort of, yeah, it's either like bad joke by nature, that there is exactly this fluctuation here now, really not letting us rest, putting to rest this galactic. Like if antiprotons would just rule this out neatly, you know, we would sleep better and we would say galactic center excess is not due to dark matter. However, now we cannot say that yet. So these are the limits from 2016. Most recently, in 2022, Calor and collaborators redid the limits, taking all systematic uncertainties into account via covariance matrices and so on. And these are the limits they come up with. So still, because this upward fluctuation limits do weaken in this parameter, in this mass range, again, where exactly galactic center is. Some other groups, by Mattia, for example, his talk was on Monday, find somehow disregard those excesses and find much stronger limits. So debate is still ongoing. And in the last few minutes, I will just tell you about neutrinos. So neutrinos can be used to look for elastic scattering of dark matter. I will not talk about that. I just wanted to mention that it's interesting that in the PV range, where we expect decaying dark matter, because self-annihilations are sort of forbidden by unitarity, like cross-section would need to be too large and one would arrive in non-perturbative regime. But if you assume decaying dark matter decaying in PV range, then neutrinos would be the first channel we would observe, because opacity of the universe is such that at PV energies, gamma ray horizon is up to galactic center or so. So first you would expect neutrino signal should be the largest. And this is also where IceCube has great sensitivity. So when IceCube data first came out, so this was 2015 or so, or sorry, 2012, it was also one of the things the dark matter community looked into. Could isotropic neutrino signal also be signal from decaying dark matter? Of course, there is lots of astrophysics and so on, but this is just a food for thought that neutrinos are actually the most powerful channel for these models. And in fact, because IceCube now has lots of data and also some handle on astrophysical backgrounds, the limits. So here are limits on decaying dark matter. So you exclude, the time scale is like 10 to the 30 seconds lifetimes or so. Oh, sorry. Yeah, exactly. And you see that IceCube limits are the strongest in this dark matter range of TV, the hundreds of TV to PV range. Okay, so this is where neutrino searches and neutrino probes really shine. Okay, so I'm coming to the end of my talk. So what the future holds? So we will have new experiments. So here is again UCAPT by year, optimistic, and for some experiments by year when they should come online. And we have, direct detection experiments, cosmological probes. Then we have Vera Rubin Observatory, CTA, SKA, all very, very relevant for dark matter searches. At the same time, also these sheer amounts of upcoming data and the fact that we want to do multi-messenger also call for new techniques. So again, here is just this question mark because I find this interesting topic as well. If we would need new techniques to deal with all this data and to look for dark matter in a new way. It's not clear to me the answer yet, okay? But the fact that we do have lots of data and we want to combine them in meaningful ways, and we also want astrophysics. We are learning so much that we have to accommodate all this complexity in the backgrounds. I at least think it's a good question to explore if new techniques are needed. Okay, applications are starting slowly in this field. I just put here one example that my group is working on, but there are others. This is, for example, automatic source detection and classification from raw LED images. So once trained, the algorithm can find the sources on the sky and decide on their class. For now, based only on gamma ray data, but this algorithm is fast, is more robust to background model, and then extension to multi-wavelength, at least in theory, is natural. Then, of course, it has its challenges, but maybe easier than in classical approaches, at least more automatic. Okay, and so this I stop here. So I hope I convinced you that this is, searching for dark matter in astrophysical data is exciting, multidisciplinary field, and there is lots of data to play with. Significant probes are made for WIMP models, and the search is widening. We're really looking everywhere we can. And right, so this is just a little comforting phrase for us dark matter people, that it always seems impossible until it's done. Let's hope so. Okay, thank you.